You ever wonder how your bank keeps your money safe online? Or how your private messages, actually stay private? Well, it all comes down to this one single revolutionary idea that completely changed the game. So let's dive into the two key revolution. It really all starts with a question that's as old as secrets themselves. How do you get a message from you to someone else, knowing that people might be listening in and be totally 100% certain that only your intended person can ever read it? For centuries, the answer seemed obvious. Just use a single secret key. But, that simple solution had a massive, fatal flaw, a problem that seemed absolutely impossible to get around. This is what we call symmetric encryption. Think about it. You use one secret key to scramble up a message, and the person on the other end uses the exact same key to unscramble it. It sounds simple and straightforward, right? But there is a huge catch. And there it is. How do you get that secret key to the other person safely? I mean, if you just send it in an email or a text, anyone could grab it. And if an eavesdropper gets the key, they get all your secrets. This is the key distribution problem. And for the longest time, it was a total deal breaker. So the world really needed a new way to think about this, a way to create a secret without having to share a secret first. And that brings us to a tale of two keys. So the big breakthrough happens in 1976. Two researchers at Stanford, Whitfield Diffie and Martin Hellman, they published this paper with an idea that was so wild, so completely counterintuitive, it basically seemed like magic. They asked, what if, instead of one shared key that everybody has to protect, what if everyone had their own pair of keys? Two keys that are mathematically tied together but do completely different jobs. And here is the genius part. You get a public key, one that you can shout from the rooftops. You can give it to anyone, post it online, whatever. This key is only for locking messages. But then you have a private key, one that you guard with your life and never, ever share. And that private key is the only thing in the universe that can unlock messages that were locked with your public key. Let's break that down. The old way, symmetric encryption, that's like having a single key to your house. It works, but if you have to make a copy for a friend, you're taking a huge risk. This new way, asymmetric encryption, that's like having a mailbox with a slot. Anyone in the world can drop a letter in, but only you, with your private key, can actually open the box and read it. See, it completely solves that risky key sharing problem. Okay, I know this might still sound a little abstract, so let's use a fantastic real-world analogy to make it all click into place. I want you to imagine your public key is an open padlock. You can make millions of copies of this open padlock and just hand them out to everybody you meet. But your private key, that is the one and only physical key that can pop open any of those padlocks. You never let that thing out of your sight. So let's see how this works. Let's say Bob wants to send a secret message to Alice. He just asks Alice for one of her open padlocks. That's her public key. He writes a secret message, sticks it in a box, and snaps her padlock shut. Now, that box is completely secure. He can send it any way he wants, regular mail, courier, whatever. Even if someone intercepts it, it's useless to them, because the only person on Earth who has the key to that padlock is Alice. And that is exactly what's happening digitally. Bob uses Alice's public key to encrypt his message, basically turning it into unreadable gibberish. That scrambled message can fly across the entire internet in plain sight. But the only thing that can turn it back into a readable message is Alice's private key, which, remember, has never ever left her computer. So we get how it works, but why was this so incredibly revolutionary? What did this idea really make possible? Well, it really boils down to two huge advantages. First, that whole key distribution problem we talked about? Gone. It just vanishes. You never have to send your most important secret, your private key, to anyone, ever. And second, it makes secure communication incredibly simple. You don't need a different secret key for every single person you talk to. You just need your one pair of keys, and you can talk to the entire world securely. This is the fundamental principle that makes the whole thing work. The public key is for sharing. It's public. The private key is for you and you alone. That separation, that asymmetry, is the entire source of its power. Of course, it's not actually magic as much as it feels like it. It's math. To be specific, it's a very special kind of math problem that's super easy to do in one direction and nearly impossible to do in reverse. The security of this whole system relies on a concept called computational infeasibility.
It's a fancy term that just means, yeah, you could theoretically guess the private key if you have the public key, but it would take the fastest supercomputers we have today billions of years to do it. So it's practically impossible.
Think of it like a one-way street in math. Multiplying a few prime numbers together is incredibly easy for a computer. For example, what's 41 times 61 times 101? A computer knows instantly the answer is
252,601. Simple, right? That's the easy direction.
But what if you try to go backwards? What if I just give you the number 252,601 and say, okay, find the original prime numbers that made this? That's really, really hard. Now imagine doing that with prime numbers that are hundreds of digits long. That is the one-way function that makes public key cryptography so ridiculously secure.
So is this amazing two-key system used for everything? Well, not quite. All that complicated math makes it a little bit slow. So in the real world, most systems, like the web browser you're using right now, do something really clever. They use the slow, super secure two-key method just long enough to securely agree on a brand new one-time use secret key. Then they switch over to the much faster single-key method for the rest of the conversation. It's the best of both worlds.
This two-key revolution literally built the foundation for our secure digital world. But it leaves us with this one massive question for the future. As our computers get exponentially more powerful, especially with quantum computers on the horizon, will the math problems that protect us today still be impossible to solve? What's the next revolution we're going to need to protect the secrets of tomorrow?